maybe you might have learned somewhere, eigenvalues and eigenvectors. To find eigenvalue and eigenvectors, do you remember this formula, this equation? Do you all recall seeing this? Given a matrix A, and you're already told that the eigenvalue lambda 1 for 3 by 3 matrix, you get 3 eigenvalue. For each eigenvalue, you have a set of eigenvector. Lambda 1 is 1, let's say this is eigenvector, eigenvalue, and then the corresponding eigenvector happens to be minus 1, 1, 0. So 2, 1, 3 is a matrix A. Multiplied by the eigenvector is equals to eigenvalue. In this case, eigenvalue is 1. Okay, if lambda 2, let's say that you have another eigenvalue, let's say this lambda 2 is 2. And if the corresponding eigenvector is minus 3, 1. Two, 1, 3. So this is the matrix A, and this is the eigenvector x2 bar, so x1 bar. If you multiply it, you will get if you do the multiplication, you will get like minus 6, 2. So minus 6, you can factor out the 2. You factor out a 2, it's going to be minus 3 and 1. So we notice like these two are the eigenvector, the original eigenvector. So this is matrix A multiplied by eigenvector x2 bar is going to give you 2 times x2 bar. This can matrix times eigenvector is equals to eigenvalue times eigenvector. Similarly, let's say if you have lambda is 3, lambda 3 is 21. we have the corresponding eigenvector. Equals to what? Please calculate, please, all of you. It's a typo error here. Okay, with this typo error fixed, it should be 21, correct?
Yes, sir.
Okay, the
Yes,
next one, how about somebody try please? What should be the next entry? How about Bernard? I'm sure you'll say don't know. If you keep on saying don't know, I don't know what's going to happen. What's the next one?
126.
Okay, 126. Good. Okay. Is equals to, now you factor out the 21, you get 1, 1, and then you will get 6 here. So if you look, again, you will get matching eigenvectors at input and output. So this is A matrix multiplied by X3 bar, X3 matrix, which is the eigenvector, is equals to eigenvalue 21 multiplied by the eigenvector. Therefore, from this example, do you have anyone got any question?
no, sir.
No, sir.
From this example, therefore, an eigenvector vector of a matrix or matrix A is a non-zero vector vector X such that for some number lambda, we have the following relationship. Matrix A multiplied by the vector, eigenvector is the number which is called eigenvalue multiplied by the eigenvector. We call lambda, lambda an eigenvalue. Okay, any question? This is just a review that I'm doing. Any question?
No, sir.
Okay, let us go and do a small example. This example also is a review. Okay, this is also part of the review. Example, find the given a 2 by 2 matrix to find the eigenvalue. This is what we used to do. Take the magnitude. This is called the determinant. Set the determinant equals to 0. So this is from mathematics 1A stuff. So if you know how to solve this determinant, you just cross multiply and set it equal to 0 and find lambda. Okay, this is how you solve. For 2 by 2 matrix, you get two eigenvalues. Lambda 1 is -2 and lambda 2 is equals to -1. So this is how you solved the eigenvalues from mathematics 1A. So any question about this? So I'm just doing a review here. Any question?
Sir,
Mhm.
why you putting -2 in front?
-2
Yes, sir.
for lambda 1.
No. For the -2 bracket 2 minus lambda, that part.
The reason why I'm getting this minus here is because I'm making this plus here. So since I'm pulling out the negative sign from here,
Okay, sir.
Yes, sir, but why there's -2?
-2 over there, sir.
-2.
In
Oh,
front,
there's no
sir.
negative. Sorry, this is a typo error. Yeah, there shouldn't be a 2. Good question. Keep it up, guys. There's no -2. Thank you for noting that. Okay, now we found out 2 eigenvalues. So which one is the dominant eigenvalue in this case? Which one is the dominant eigenvalue?
Lambda 2.
Lambda 2, sir.
Lambda 2. Okay. A good guess. Which one is the dominant? Okay, you guys, of course, you know, -1 is bigger than -2. That's why you said minus lambda 2, right?
Yes, sir.
But actually, we are looking at the magnitude of lambda 1. Okay, magnitude of lambda 1 is 2. Magnitude of lambda 2 is equals to 1. So here we are going to look at the magnitude. Apparently, lambda 1 magnitude, lambda 1 is greater than lambda 2, the magnitude of lambda 2. So therefore, in this case, lambda 1 is the dominant eigenvalue. It's a dominant eigenvalue, lambda 1. So we have to go through all this process to find in mathematics, engineering mathematics 1A, this is the conventional way of solving the eigenvalue. We have to solve and then find out all the eigenvalues. And then we decide which one is the dominant eigenvalue. Let's say if you have a 3x3 matrix, there's a lot of work to do. It's easy to make algebra error. So therefore, we're going to come up, there's another way of doing things without going through all this. You directly go and find the dominant eigenvalue using the numerical analysis technique. Okay, let's say in this example, you found the dominant eigenvector . So now what is the dominant eigenvector? What is the dominant eigenvector of A, vectors of A, corresponding to The dominant eigenvector is defined to be the eigenvector corresponding to the dominant eigenvalue. So you go and find the eigenvalues first, and then decide which one is the dominant one, and then you find the eigenvector corresponding to these eigenvalue. Do you remember how to find the eigenvector? Find the eigenvector. So this is how we usually find the eigenvector. We say A, matrix A multiplied by the vector equals to lambda 1 multiplied by the vector, which is supposed to give you the eigenvector. So Ax bar minus lambda 1 x bar is equal to 0. Then you have to solve for this. Solve for A minus lambda 1 x bar equal to 0. The bar stands for matrix. Missed the Okay, this is how you solve for the eigenvector. Remember, there's a difference. When you find the eigenvalue, you had the magnitude, right? You were solving for the magnitude. But here, there's no magnitude. You are finding the determinant. You are solving the determinant to find eigenvalue. But here, it's not the determinant. So simply solving for this equation. So I'm not going to go through this in detail because this is just a review. In this class, you won't be tested in this method. I'm just doing a review. But still, you have to need to know how to perform simple matrix operation and all that. So we already know lambda 1 is minus 2. You replace the lambda 1 with the minus 2.
Minus 12, sir.
Beg pardon?
Minus 12.
Oh, minus 12. Thank you very much. Equation 1 from 2. From equation number 2, x1 can be solved. And as x1, x2, x1 is 3x2. So you replace your x1 with 3x2. And x2 and x2 is simply x2. I'm not going to just rewrite that as x2. Just leave it as x2. Next, you factor out the x2. It's 3, 1. X2 is not equal to 0. So this is the eigenvector.
Sir,
Yes.
so why you said no need to plug in into equation 1? Because you will get 0.
No, because see, I don't need to plug in because I'm solving for x1 in terms of x2. If you look here, I'm solving x1 in terms of x2, and then I'm replacing the x1 is 3x2. Okay. So since this is already in x2, what do you need to do for this matrix? You have to leave everything in terms of same variable. So since I have my x1 in terms of x2, x2 it will not change. Just leave it as it is. So everything will be in terms of x2.
Okay, sir. Thank you.
So this is how we usually solve for eigenvalue, eigenvector. There may be another way to do it. And then we pull out the common x2. So only when you leave it everything in terms of x2, you can factor out the x2. So the eigenvector. So this is from Engineering Mathematics 1A. In this class, we are not going to be doing this. Okay, I'm just doing a review. I haven't done the numerical method yet. We're going to do it after we are done with this. Good question, good question. Any other questions? So you have any doubts, this is the time to do it. For eigenvalue, lambda 1 is -2. The eigenvector vector x bar is equals to x2, 3, 1. So similarly, at lambda 1 equal to -1, you can derive a corresponding eigenvector, right? But we are not going to do that because we are only finding the eigenvector corresponding to the dominant eigenvalue. This is the eigenvector corresponding to dominant eigenvalue. Is there any question? The thing is, what I'm pointing out here, this is just a review. So in order to find a dominant eigenvector or eigenvalue, you have to go through the entire process of finding the eigenvalues first. And then you'll decide which is the dominant eigenvalue. And then you use the eigenvalue to find the eigenvector. But there's another way to do this by numerical analysis. So I'm going to show now how to do that using the numerical techniques. So example, how to do that, how to find a dominant eigenvector using a numerical method. And this is also called power method. How to find dominant eigenvector using numerical method. Power method. They call this power method. Okay, using the same matrix that was given earlier. Now the question is approximate. So we're already done with the review here, okay? We're already done with the review. The numerical analysis starts below here. Numerical method. We call this power method. In this case, we are doing power method here. Okay. So in this example, you want to do approximate a dominant vector using numerical method. Given, do 6 iteration given matrix A, two minus 12, 1 minus 5. It's the same matrix that we used earlier. Now we're going to use the numerical analysis to find the dominant eigenvector. As usual, we have to do certain number of iterations so that the solution will converge. Here you're asked to do 6 iterations. Okay, the first thing, begin by guessing an initial non-zero vector x naught. So I'm guessing my initial eigenvector is 1, 1. So this is something that you can guess. If you want to guess non-zero value, so you can guess 1, 1 or 2, 2 or 3, 3. But it will be easier to start with something small and easy to perform operation with. So we start with just 1, 1. And you see the answer will converge to the actual eigenvector, dominant eigenvector. Then you carry out, any questions so far? Then carry out the following iterations. Iteration 1, call this x1 bar, is matrix A multiplied by your initial guess. So that's going to give you -10, -4. So this class, if you have to know how to do matrix operations, simple matrix operations quickly. So now if you look, if I factor out -4, I can say if I'm going to factor out the smallest magnitude 4. So this is going to be -2.5 and 1. -1. So I can factor out the minus sign also. Very easier to do our operation without minus sign. Factor out the -4. Then next what you do? You do the second iteration. Matrix A multiplied by the previous iteration, eigenvector obtained from the iteration 1. Okay, for x1 bar, what are you going to put? You're going to put this, inside here. -10, -4. (28:10). Factor out 10, smallest magnitude. Then next, what do you do? Will be the A multiplied by x2 bar. Factor out the smallest magnitude and the sign.
-3.
Beg pardon? Any question?
No, sir, no, sir.
Involved. You just keep repeating until you reach the 6th iteration and then you stop. Because the question say, when you come to x6, you can stop at 6th iteration. We are stopping at 6th iteration because, as you can see, we started with the initial guess. Our initial guess is here, right here, the initial guess. We start with this initial guess, and then we moved, and then this is, first is, it became 2.5 and 1, and then 2.9, 2.91, 2.96, and then 2.981, and you see the answer is converging to 3.1. You can move on, do many more iterations to get an accurate value. Eventually, from the previous exercise, we know our eigenvector is 3, 1, right? From the previous. So from the previous value, we already calculated the eigenvalue 3, 1 without using the numerical analysis. Numerical analysis is not going to bring you right to 3, 1, but it's going to converge slowly to 3, 1. So if it's converging to one specific value, then you can stop it. You're happy with it. So similarly, so it's coming very close to 3. You can continue some more. You can get many more decimal places. Depends on how much accuracy you want. So we are launching a rocket to moon. Then you want to be more accurate. Because if you're not accurate, instead of landing in moon, you land in the sun. That's just a joke. Okay. By the time it reaches the sun, it will be burned out, right? Before it can get near to the sun. Anyways, the idea is that you guys get the technique. You do this until you converge. And then you can say your eigenvector, this is your eigenvector right here. Previously, similarly, like this is, actually this is the x2, it's outside the eigenvector. This is actually the eigenvector right here. After the 6th iteration, next example, approximating a dominant eigenvalue using numerical technique. So we're going to use a formula called Raleigh. It's a formula to find the dominant eigenvalue. This matrix A multiplied by the vector eigenvector A times matrix. Okay, let me write this out first. So this is a dot product. X bar dot with X bar. I'm putting this. So matrix A multiplied by the X dot product with X. Divide by X dot product with X. So you all know how to do dot product. For example, when you have two vectors, for example, you say you have a vector X, which has say X1 component and X2, and you have Y bar, Y1 and Y2, then X, matrix X, dot product with the matrix Y, is going to be x1, x2, a dot with so you're going to be just doing this. What are you going to do? You're going to multiply x1, y1 plus x2, y2. That's the dot product. So this is just for review. From previous example, we know that matrix A is 2, 1, minus 5. And then we found out on the 6th iteration, the eigenvector is 190, 2.99 multiplied by 2 vector 100. So this is the vector we're going to be using here. So in this problem, we're going to our x is actually the x bar in this problem. Let's go ahead and calculate A, matrix A multiplied by x bar. X bar is 2.99. Okay, I'm talking about this actually, not this one right here. I'm talking about the x bar here. Any question? No question? Good. So if you know if you can multiply a matrix, this is how you usually check. If you have a 2 by 2 matrix on the left side, on the right side you get 2 by 1 matrix. So you have to come and check if these two are compatible. If these two are the same number, then you can do the matrix operation. The resulting matrix will have this dimension. The resulting matrix. This is checking is compatible or not, whether you can perform this operation. Compatible, checking compatibility. I don't know if this is the right spelling, but it's okay. So after you perform this operation, so you're going to get so this is matrix A. So please focus on the technique. There may be some algebra errors. Okay, don't worry about that. What is important is the procedure. So is this okay so far? If any problem, then you talk. If no problem, then it's okay. Silence is accepted. Okay, next what you do, so you already find your AX. Next, you have to do this. You have to do all this. In order to find lambda, you have to find AX bar. Next, you have to do this, AX bar dot with X bar. Then next, you have to do X bar dot with X bar. And then you divide this by this. X bar dot with X bar. Dot product, so this is the dot product. So this is a dot product. So earlier I mentioned how to do the dot product. Multiply by the same components. In this case, x1, you can consider this. You may consider this, for example, x1, x2, x1 and x2. Like for example, this also x1 and x2. x1 multiplied by x1 plus x2 multiplied by x2. One. So that's going to give you how much is that? 2.99 multiplied by 2.99 plus 1 times 1.
9.9401.
9.9401. Okay, thank you. Okay, next is after you we also have to find this AX bar dot with X bar. AX bar, we already calculated this earlier, idea, so minus dot with Okay. Using all this information that we just computed, now you calculate Raleigh. Raleigh, I don't know how to pronounce this. Calculate the AX bar dot with X bar divided by X bar dot product of X bar. That's going to be equals to minus 20.09.94. Is equals to minus 2.01. So lambda is minus 2.01. Which is a good approximation of the dominant eigenvalue. Okay, that's a direct way of finding the eigenvalue. Okay, that's also another way to find. You do an initial guess, and then you do your first iteration, and then keep substituting, and then bring this forward here, and you do your second iteration, and then whatever you get, you bring over here. And then what do? After you're done with all these iterations until here, I'm doing here until the 7th iteration. After you're done with the 7th iteration, then you try to do the iterations of the lambda. First iteration, called this lambda 1, this entry here, and then if you look at this entry, 10 divided by minus 4, you get lambda 1. And the next one will be, again, we look at the current output on the second row, divide by the previous output on the second row, and then you get lambda 2. Similarly, when you continue with this, you will see the answer is converging to minus 2. I will upload these notes later on. Maybe you guys can look over. But
Bye. Thank
Bye,
you.
sir.
Thank you,
Thank you,
sir.
sir.
thank you. Bye.
Thank you, sir.
Thank you. Bye.